Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about cross entropy and KL divergence. Let's set up the agenda first. So I hope the screen is visible. So we'll discuss about cross entropy and KL divergence. That's the and all the topics within that. So the agenda is first we'll define what is information because all these topics come from the field of information theory. And then we'll understand what is entropy, then cross entropy, then KL divergence and JS divergence. KL is Kullback-Leibler divergence and JS is Jensen-Shannon divergence. Jensen-Shannon divergence. Okay, so let's go one by one. So we'll understand each and every topic. The first thing, so let's set up the theme. So as I mentioned, all these topics, okay, these are very important for machine learning and these come from the field of information theory. So these come from the field of information. There's a field of maths called information theory, and these concepts are borrowed from there. So machine learning borrows concepts from many fields, and this is one of those fields. So we borrow these concepts from information theory. So what is, first of all, let's understand what is information or surprise. Okay, information or surprise. So what's the literal meaning of surprise? Let's understand that. For example, if you see a very common event, will you be surprised? No, right? And if you see a very rare event that doesn't happen, then you'll be surprised. That's how we measure surprise, right? Common events, not surprising. Rare events, that's surprising. And so what's the probability? And if you want to understand that in terms of probability, then so the probability of a common event is very high, right? So if we say probability of a common event is very high, and probability of a rare event is very low, right? That's what it is. And if there is something common that is happening in terms of information, if you want to understand, so if there is something common, means it is not providing me any much information. For example, if we understand it with respect to height of people in a country, so if most people are of average height, so if you talk about India, they're around 5, the height is about 5 feet 6 inch or something. So if I see anybody around 5 feet 6 inch and close around that 5.7, 5.8, okay, you won't be surprised. But if you see a rare event, if you see a person is 7 feet tall, or anybody who's more than 6.5 feet, that's the rare event and that's surprising. But that gives you more information also. The rare event gives you more information, okay, that such people can be so tall also. But if something is very common, everybody is so of the same height, around 5 feet 6 inch. So it doesn't provide you much information. So that is with respect to information. That if something is very common, it doesn't provide you much information. And if something is rare, it extends your range of information that, okay, such an event can also occur. So in terms of probability, if we say, so probability, as we understand, probability of a common event is very high. Probability of a rare event is very low. How do we understand it in using, how do we define surprise then? So surprise factor, this is defined as, okay, so as negative, okay, we write it as x, negative of log of probability of that event. Okay, let's understand this. Why log? Okay, so this is very useful. If you see, you will see in machine learning everywhere log is used. Okay, so that's why it's a, and this is the probability. Okay, this is to give it a range. I will not go into the depth of it, so let's take it on the face value that we are using log of the value, and let's understand the details. The probability of x, so if it's a common event, okay, probability of a common event will be very high. Say for example, if something is very common and if it will happen only, say for example, if I have a coin which gives heads, it has heads on both the sides, so whatever you do, it will give you head. So probability of head will be equal to 1. So log of that probability, so what will be the surprise factor here? Surprise factor of this event will be minus of log of probability of x. We take log because log is a monotonic function, means as x increases, log of x also increases. We can say that, right? So as x increases, log of x also increases. So that's why we can replace x with log of x. So the probability of x will be replaced by log of x. Okay. So now let's come back to the example. So we have a coin, okay, unfair, which has head on both the sides. So probability of getting a head is 1. So log of 1, what will be log of 1? Surprise will be log of probability of 1. Means log of probability of x, probability of head is 1. So surprise will be 0. Yes, it is head on the both sides. So we won't be surprised. So that's how it is defined. And say for example, in the same coin, what will be the probability of seeing a tail? This will be 0, right? Because there is no tails at all. So if I have to measure the surprise for this, so surprise for this event tails will be equal to minus of log of 0. What is log of 0? Log of 0 is minus infinity. And minus of minus is infinity. So log of 0 is minus infinity. The graph of log is something, it comes here and it goes like this, it increases. So at 1 this is 0, and at minus infinity this is your x, this is y, or log x, y equal to log x. So at 1 it will become 0, and then it keeps on increasing, and it touches minus y-axis at minus infinity. Okay, so this is how it is. So coming back to this example, so log of 0 would be minus infinity, and negative of that is infinity. Means if you see a tail in a two-sided coins which has both the sides as head, you will be infinitely surprised. This should not happen. Okay, so this is for understanding. So this is how surprise is defined. So surprise of x is defined as minus of log of probability of x. I hope surprise is clear. And the same thing I talked initially, right? So that's what will give me the information also. More the surprise, higher the information I'm getting from an event that has happened. Okay, both are proportional. From now I will just use the term surprise. So this is a surprise. So we have defined what is surprise factor. That is negative of log of px. Px is a probability. Okay, now let's move to the next topic. So what is entropy now? Entropy in general measures randomness. This is the word. Okay, it's a measure of randomness of a system in terms of probability, how random the things are. For example, if I have a fair die, so probability of observing 1, 2, 3, 4, 5, 6 will be 1 by 6. Okay, if it's a fair die. Similarly, if I have a fair coin, okay, so probability of head is equal to probability of tail is equal to 0.5. If I have a biased coin, where I see that probability of head is higher, that is 0.9, probability of tail is equal to 0.1. So if I get a heads in this biased coin, will I be surprised more? Or if I get a tails, will I be surprised more? Definitely if I get a tails, I'll be surprised more, because probability of tails happening is very low and heads is very high. As I said, head is common, less surprise. So surprise factor for head is low, and for tails it is very high. For heads is low, surprise factor, and for tails it is very high. So it depends on the probability. So what does entropy measure? So entropy measures the average surprisal of a distribution. So all these are distribution, these are uniform distributions, right? So this is uniform distribution. We have studied this. Uniform means all the values are equally likely. Here also this is a uniform distribution. Heads and tails are equally likely. But this is a biased, this is not equally, this is biased. Okay, so let's now calculate let's define what is entropy. So this is what is entropy? How do we define that? Entropy is an average surprise of a distribution. This is measured, it measures average surprise of a distribution. Distribution is this distribution that I'm talking about. This is uniform distribution. Okay, similarly we can have Gaussian or whatever, all the distributions that we know. So this gives me the average surprise of a distribution. Okay, and in terms of information, we can say that how much information do we get when we see a particular event, how much more information is this event providing me. So that's what entropy means. Okay, and if the events are more uniform, means everything is very equally likely, so the entropy will be more, because everything is like in heads and tails, right? If this heads and tails like both are equally likely, so the entropy will be more randomness. I can get a head or a tail, or head or a tail, I don't know, its chances are 50-50. But if I have biased coin with a 0.9 probability I can get heads, means this is the entropy of this is low, because mostly I'll get heads and tails I'll get very few times. So the randomness here is very low because heads is dominant, and we know that 9 out of 10 times I'm going to get head only. And it won't provide any much information also, because I know it's a biased coin, mostly I'll get head only. 90% of the times I'll get head only. So this is less random than this, and entropy is a measure of that. And if we write it in the terms of formula, how do we write that? So the symbol is, we write it as h of p. Okay, the symbol is h of p. P is the distribution, underlying distribution of that event, is equal to, let me write it, is equal to the expected value. Okay, expected value of the surprise factor, of the surprise what we have. Let me write it this way. So this is the expected value of, so the expected value we know, right? Expected value is the average. So the expected value will give me the average of this. So expected value of the surprise, this is my surprise factor. Let me write it down. You have seen this is surprise factor. So what is the average surprise of a distribution? It gives me this. And this is, for example, this p is this, that x has the underlying distribution of x is p. Okay, that's the probability distribution of x. So what is the expected value? We know the formula, right? Expected value of something is, so this is a negative, remember this negative sign, don't forget this, negative summation of all, because it's the average, right? So summation of probability of x into log of px. Okay, so this is the formula for expected value. Probability of each event into, and this is surprise factor. This is what we are calculating. This is the expected value of log px is log px into probability of log px of that event. So this is how my, and with a negative sign, because this is coming from the surprise factor. So this negative sign gives me the surprise. I hope this formula is clear. Let's understand this with the example. So this is my h of p. This is your entropy. Entropy. Okay, this is probability of x, self-explanatory, and this is your negative surprise factor. Okay, so let's see with an example. So again, we'll come back to the coin only. That's a simple example. So for example 1, toss a fair coin. Fair coin. So probability of heads is equal to probability of tails is equal to half, or 0.5. This is a fair coin. So what will be the entropy? So first let's calculate the surprise. What will be the surprise for this? Surprise is equal to surprise of heads. Okay, let's do of heads first. Is equal to minus log of probability of head. This is equal to minus of, what is the probability of head? Half. And let's assume all these are information theory. So everything I will take it as on the base 2. Okay, because 0 1 0 1. Okay, so I'll take it as log of base 2, and this is 0.5. 0.5 can be written as 2 to the power minus 1. This is 2. So this minus 1 comes in front. So this is minus 1 into minus. So this, you see, right? Minus 1 comes here. So minus minus plus, because log power comes here in the front, right? I hope you remember log. So this will become log 2 of 2. This is equal to 1. So surprise of h is 1. Similarly, this is half. So surprise of tail, similarly, surprise of tail will also be 1. These are all log base 2. I'll be discussing all these examples today that will be using log base 2 only, because that's from information theory. And this is measure, so this is 0 and 1, right? To measure, because information theory everything is bits, and this is also measured in bits, so this is 1 bits. This is a unit of measurement of surprise, and everywhere wherever this surprise will be there, right? So that is the unit coming out. Everywhere will measure the things in bits only when the base is 2. When it's natural log, the unit is different. I don't remember now. Probably I'll write it down, or you can check it. Surprise of tails is also heads. Surprise of tails is also 1. So we saw this. Now let's take the second example. Biased coin. Probability of heads square is 0.9 and probability of tails is 0.1. So it will be surprise for heads. Surprise for head will be minus log of probability of head, that is equal to minus log of 0.9. What is log of 0.9? Of base 2. We'll be calculating on log of base 2. So you can calculate that easily. I have this, but I'll just show you how to do this. Future I will just use it. That is log 2.9. So this is equal to minus point, and that minus is there, right? So that is only for log 2, and that negative is there. Negative is there. So this will be equal to 0.15 bits. So if you see this, it is very low, very close to 0. It is close to log 1. Log 1, 0 is like no surprise. So this is very close because 0.9 is very close to 0.1. So getting a heads is very low surprise. Okay, low surprise, very common because 0.9 is there. So this is here low surprise, common. Similarly, what will be the surprise for tails? Is equal to, I'll just write it down, log of 0.1. This will be equal to log of 0.1. Let's calculate that again quickly. Minus log 2, 0.1, that is minus 3.32, and with the negative sign this will become 3.32. So 3.32, okay, is very high. Okay, this is very high. This is because 0.2 is rare. 0.15 against 0.12. This is rare. So this is our surprise. And now let's calculate the entropy for each of them. So for the example 1, okay, entropy of fair coin will be equal to, this is equal to minus sigma probability of x into log of probability of x. We saw here, this is your formula. Okay, so let's use this formula, fair coin. This is, so what will be the sigma, all the possible, over all the possible outcomes. So heads or tails, there are only 2 outcomes. So what will be the what will be this? This will be equal to, I'll just write minus outside, and then probability of x is 0.5 into, then that was, what was the probability of, both are 1, right? Here both are 1, here 1 and 1. So minus probability because of this minus 1, this was 1, right? We calculate the final value, 0.5, and this 0.5 into 1 is equal to 1. So h of p is equal to 1 for fair coin. Probability is half, and we calculated that 1 is the surprise, that is with negative log value. So we just sum that up, probability into log of probability of head and probability into log of probability of head, negative log. So this is sums up to 1. So this is 1 bit, this is in bits. Okay, so this is your for fair coin. And then similarly h of p or entropy for biased coin, where P of H is equal to 0.9 and probability of tail is equal to 0.1 will be, let's do it again. So this will be H of P will be equal to summation similarly. So we've calculated all these values. So for heads it is 0.15 bits. So it will be 0.9 is the probability into 0.15 plus 0.1 into probability is 3.32. For tails the surprise is 3.32. So this is your heads, this is your tails, this is your heads, this is your tails. Entropy for each of the value. So if you calculate this, this will come approximately to 0.47 bits. So if you see here, the entropy for a fair coin was 1 bit and this is 0.47 bit. This is low. Low entropy means low randomness, and that's obvious because here both the chances of getting a head and tail is equal, half. That's why the net entropy or randomness is higher than a biased coin where getting probability of getting a head is very high, that's 0.9. So that's why the net entropy is lower than 1 bit. This is 0.47 bit, that is less than half of it. Okay, I hope entropy or randomness is clear because this is the base. So surprise, okay, you based on that surprise we calculated entropy. Entropy is average surprise. Okay, I hope entropy is clear. Let's move to the next topic, that is cross entropy. Cross entropy. What is cross entropy? This is one of the main topics here. Cross entropy is nothing but, say for example, our data is coming from some probability distribution, okay, whatever, some probability distribution P, and we try to measure it, okay, using another probability distribution Q. So P and Q are the probability distribution. This is the original probability distribution, and we are trying to measure this using this a different probability distribution. Okay, so the actual value is of this probability distribution, and we are trying to measure it using the another distribution which is Q. So how surprised we are? We will measure how surprised we are if actually it is the entropy means actually the values in that of that random variable is coming from distribution P, and we try to measure it using another random variable Q. And why is this important? Because in machine learning we don't know what is the actual distribution of our random variable or whatever things we are measuring, what we were trying to model. So we don't know that, and we hypothesize that we have another model which has its own distribution, and we try to predict the values of P using our model's output, okay, using Q. So this gives me the cross entropy. Okay, actual is P, but I am trying to measure it using Q. So this is a cross information we are trying to get. The actual is this, but I am trying to predict the values using Q. If actual is P, this was the entropy, and if I am trying to use come through another model which I don't know, which I am trying to approximate and see, is this model giving me the actual value? This is the actual, and I am trying to measure it using Q. Then that is your cross entropy. How much is the randomness when I am trying to measure it using another distribution, which is my model's distribution. In general, that is your example, but in general, this is measures how surprised we are on an average if truth is P, but we predict it using Q. If the true model is, if the true underlying distribution is P, and we try to predict the values using another probability distribution Q. So let me define it for you. So what it is? This measures, cross entropy is the measure of how surprised, everything is in the terms of surprise only, surprised we are on an average if truth is P is the distribution, and we measure or we predict using Q. Okay, so P and Q are different distributions. So this is, as I mentioned, actual surprise from our model's prediction. We don't know what is the underlying distribution of the data, but we have our model which is telling that this is the distribution, and we try to predict the values, and that's where in the models We use this cross entropy loss a lot. You must have heard. You will in the further videos and machine learning, people who know that they use cross entropy loss. Okay, and this is the cross entropy. This is the meaning of the cross entropy loss. Okay, so how's it given? So let me write it down. So this is given as h of p comma q. Okay, so this is h of p comma q. The actual probability distribution is p, and I am measuring it, trying to predict it using q. What is the measure of the surprise? So average again. So this will be expected value of. So I am measuring it using q. So the surprise will come from here, qx, and this is my. So this is my cross entropy, and this actually the distribution of x is coming from p. This is my actual distribution, and this is my surprise factor. This is my surprise. And what is the expected value formula again? This is equal to summation over negative will come out, negative I'll take it out. I equal to 1 to n, all the values what I have. Probability of x into log of q of x. Okay, so let me write it I. So that because I is, I have mentioned I here. Okay, this is my I. This here. Cross entropy. This is the, in terms of entropy, this is the how we write it. Entropy of p when we measure it using q. The underlying distribution is p, but I'm measuring it using q. So the surprise will come from q, and the probabilities will come from. This is the probability of all the individual events in the distribution. Okay, the random event. So let me give you an example to understand this. Okay. So this is the definition. I hope the definition is clear. This is your cross entropy formula. Let's see the example. For example, okay, let's see, we have a model which is used to classify images as simple cats and dogs. Okay, a model to classify images as cats and dogs. Okay, so if I so for an image, okay, for an image, say if it is an image of a cat, so what will be my outcome? The true distribution will be probability of a cat. Okay, the true images is cat. So the distribution will be, how will the distribution look like? Distribution P will be equal to 1.0 for cat, or 1 for cat, and 0.0 for dog. So this is my original distribution. I know that this is 100% cat because this is how I have labeled, and this is 0% dog. Okay, and let's see how compare, okay, two models, okay, cross entropy of two models, which will give me the idea of cross entropy loss. Okay, so I have two models. So the first model's output is, so first model is model A. Okay, and for this the output Q of A is that it is 0.8 cat and 0.2 dog. So this is what it is predicting, that cat is this and dog is this. See, this is my prediction. This is the probability of that. This is telling, originally we know it's 100% cat, but my model says that 80% cat and 20% chances that it's dog. That's how models predict. So now, what will be my cross entropy? What will be my cross entropy for this? So this is my actual P, and this is my model Q's prediction. So this is the actual prediction, okay, and this is my model Q's prediction. So let's see what is the cross entropy. This is the actual entropy, this is the predicted entropy, and let's see what is the cross entropy, actual versus predicted. So how will we write it? H of P comma Q of A, this is equal to sum of all negative summation P of x log of Q of x. Okay, this is the formula. So what will be H of P comma QA? I'm writing it now. So there are two possibilities, cat or dog. So let me sum it up, minus So actual probability of cat is 1 into log of, what is it predicting? This model is predicting 0.8 plus other option would be, what are the options? That it might be a dog, that is with 0 probability, that's the actual probability. So P of x is, that is the actual probability coming from here, 1 for cat and 0 for dog, and this is the predicted, this coming from 0.8 from here, and for dog it is 0.2. Okay, so this is 0 into log of 0.2. This is my negative outside common to all. So this will be equal to, so this is 0. So this will make this whole term 0. So only thing that remains is 1 into log of 0.8, that with the negative sign. What is log of 0.8? Log 2 base 0.8. So this is minus 0.32, and with the negative sign it becomes plus. So this will be equal to 0.32 bits, negative plus negative. So this is your HPQA. This is a model A. Okay, this is very low cross entropy, because we know that it is very close. It is 100% cat, 0% dog, and my model is predicting very close, that it is 80% confidence it is telling that this is cat, and 20% is telling it's dog. So this is very close to the actual. So that's why the difference, the cross entropy between the actual and the predicted is very low, and the model is doing pretty fine here. Okay, and the model is not surprised that, okay, what I have predicted and the what is the actual thing, it is differing by much. And now let's see, there's a model B. There's a model B which is predicting that it is 0.2 cat and 0.8 dog. Opposite, this is cat and this is dog. Let's measure the cross entropy of this now. This model is saying that this is 20% cat and 80% dog. Okay, actual is 100% cat. What will be the cross entropy? Let me write it directly. So H of P comma Q of B. So actual. So this will be negative of. So actual probability is 1 into log of 0.2 plus actual probability is 0 into log of 0.8. Directly I have written the formula. This is the probability of cat, this is the probability of dog. Is 1, and this is dog's probability. So minus, okay, all is log 2 base 2. Okay, so that's implicit, everything is being done. So this will be, if you see this, right, so this will be equal to log 2 of 0.2 is minus 2.32. This is minus 2.32. Minus minus plus, so this will become 2.32 bits. If you see here, the cross entropy is very high. This was only 0.32 bits, and this is 0.32 bits. This is far off from the actual prediction, from the actual truth. So the surprise is very, very high for what is actual and what I have predicted. So the net average surprise for the difference between these two is very, very high. The model predicted that it is a dog with a high probability, but that is wrong. So that's why we're getting a very high cross entropy loss, and this value will be fed back to train the model so that we reduce this. Okay, I hope cross entropy is clear. Good. So now let's move to the next topic. Next topic is our KL divergence. KL divergence. So this is coming from the name of two scientists, Kalbach and I think Leibler. Divergence. Okay, this is the name. So this was giving me the measure of surprise when actual is P and I'm measuring it, I'm predicting the values using Q. Now when I want to find that what is the actual difference, if I have predicted that my entropy was P, okay, and and my cross entropy, whatever I have got with that, my actual was P and I was measuring using Q. So I'll get one entropy here and I'll get one actual entropy from this entropy formula, HP. Okay, this is one is relative. This cross entropy is giving me relative. That actual distribution is P, but if I'm predicting using Q, so this is giving me one value, and this entropy will give me one value. That what is the actual entropy when nothing. This is the model I'm predicting using that only. So that was my reference. It will have some entropy, and now I have a cross entropy where actual is something. I was predicting using something else, so I was getting some cross entropy. Okay. Now my Kullback-Leibler divergence or KL divergence measures that what is the extra surprise when using a different model to predict, okay, to make predictions. So I'll give you the formula, then you'll understand. So I'm telling you in words, this is telling me what is extra surprise. So there will be inherent surprise, that is the entropy, plus what is extra surprise when I am measuring that same entropy using some other model. So what is the difference in both the surprises? That's what KL divergence measures. Okay, extra surprise when using a different model or a different distribution probability in terms of to make predictions. This is very in simple terms. Instead of using the true distribution. So I'm using a different distribution. Say this is my Q and the original distribution was P. So what is the extra surprise? What is the delta between the entropy and the cross entropy? So this is your KL. So this is written as, so in other words, if I say this is the difference between the actual surprise which I got using cross entropy. This is the actual surprise that my model predicted, and what was the true value. So this was the actual surprise, and KL divergence measures the difference between this actual surprise minus minimum possible surprise. That's the inherent entropy in that distribution. Okay, so this measures, so let me write it down. So this is written as DKL. Let me use a different color. KL divergence. This is how we write it. Of two distributions P and Q, KL divergence of two distributions P and Q is equal to the cross entropy minus the entropy. Okay, so this is your KL divergence. This is your cross entropy, the actual surprise, and this is the minimum surprise. This is your entropy. This is the minimum surprise that is inherent in the system, and this is the cross entropy that my distribution was something else, but I'm trying to predict it using something else, which is my model. So this is my cross entropy, and the difference between two gives me the KL divergence, that how much extra surprise we have got because of the model or the new distribution, because of that I'm using to measure the true distribution. Okay, so this, in other words, if you say in terms of information, it quantifies the information loss. Okay, whatever the information was there actually in the system. Okay, and what I did using this, what I calculated using this cross entropy or another model or another distribution, so it quantifies this information loss. The information loss actual, the minimum information loss, and plus the minimum information that is has, and what the new distribution or the model is able to capture. So this is the loss in information. This is the delta that KL divergence tries to capture, or in other words, we can say that the penalty that we get for using a imperfect model. Okay, so let's break it down to something. What is it about? To bring it in its simplest form. So what is my cross entropy? This is your minus sigma P of x log of qx, right? And what is your entropy? Sigma. That is your expected value of the same, coming from the same distribution. This is expected value coming from the, when the distribution and the prediction are same, and have the distribution and the prediction are different. So this is what is taking the difference. Now let's expand it. Okay, so here if you see that sigma px, this is common in both. Okay, and this is minus of minus, so this is a negative term and this is the inherent minus, right? So this minus and this minus will become plus, so I'll just write it minus px log of q of x plus this minus and this minus, this will become plus, because there is an inherent minus because of the surprise factor. Minus minus plus, this will be sigma p of x log of p of x, right? So take out sigma p of x as common, and this will become log of px will come from here minus log of q of x, this will come from here. This is log px, this is the plus, this is a negative sign, this is a log of qx coming here. So what is log a minus b? That is log a by b. So this is equal to, now you see this is a positive, earlier everything was negative, and now you see this is positive. P of x log of p of x by q of x. So this is here KL divergence. This is how we write it. I hope the derivation is clear and the actual meaning behind what we do. This formula many of you will know, but this is the actual entropy, and this is the actual understanding based on entropy. So it's the difference between the cross entropy and the actual entropy of the distribution. Cross entropy is when we measure a distribution using another distribution. So that's the delta, that's the measured surprise, right? This is the minimum surprise that the system or the model, or or the distribution inherently has. Okay, this is your KL divergence. Let's, and if it is a, this is for our this is for discrete. This is for discrete. Similar formula will hold for continuous. What will be continuous? So my KL divergence will be, this will become integral, simple, minus infinity to infinity. This will become px or f of x. Okay, and log of, I'll let it be consistent, px by qx. So just the summation changes to integral. Okay, and this is just a summation. I can write I equal to 1 to n everywhere. Now the formula is clear. Let's do a simple example. So there is a note, there's something that, just note that KL divergence is not symmetric. Okay, KL divergence is not symmetric. What do I mean by that? That means that KL divergence of P, when I measure it using Q, is not equal to KL divergence of Q when I measure it using P. So this is not symmetric. This is one of the drawbacks. Because of that, we will study Jensen and Shannon divergence after this. Okay, so let's understand this. Just do the maths and understand it, so that it becomes very clear. Let's continue the cat example. For example, continue the cat/dog example. What is that? Using the same. So what was that? Model is trained to classify. So my actual predicted value was that actual P was that 1.0 and this is 0.0. So this is for, this is the actual label, cat and dog. This I know, this is the truth or actual distribution. This is how it is. The probability of cat is 1 and probability of dog is 0. 1 and 0. This I know, this is the truth. And what was my entropy? Let me measure what is the entropy for this. Entropy would be minus sigma px log of px. So all the possible values of this will be 1 and 0, cat and dog. So this will be 1 minus 1 into log of 1 plus 0 into log of 0. Okay. So this 0 into log of 0 is undefined. Okay, just note that here, undefined, because that is minus infinity. Okay, but for approximation we take it as 0. For approximation we approximate this term 0 into log of 0 as 0. So this is a hack, computational hack that we do, but in actual terms log 0 is undefined. So for computational hack we'll say that computational hack, and in general this entropy is measured a computational hack that 0 log 0 is equal to 0 or log 0 is equal to 0. In general, whenever we measure entropy, we have a condition that sum of all the probabilities should be 1. So sigma of p of x should be equal to 1 in terms for entropy. That whatever are the possible outcomes of that event, the sum of that is the whole PDF or PMF, that should be 1. And generally the p of x is greater than 0, because we don't want to measure the values which are highly unlikely. Px equal to 0 where the probability is 0, which is a rare event or an impossible or highly unlikely. We don't measure these. So px should be greater than 0. So that is where we measure entropy. But here, since we have encountered this, here we'll say that 0 log 0 is equal to 0, and we'll move ahead with that. So with this, what will this be equal to? This will be equal to log 1 is 0. Log 1 is equal to 0. We know that. We have seen from the graph also. This is equal to 0. So h of p is equal to 0. Okay. So now let's come back to model A. So what was my one model A? Model A predicted that 0.8 cat and 0.2 confident that it is a dog. So my KL divergence will be of p and q will be equal to h of p comma q minus h of p, right? This is my cross entropy. Cross entropy of cat and dog we computed earlier, right? 0.32 bits, h of p comma qa, right? This is for qa. So let me write it a everywhere. Okay. So this is 0.32 minus 0. This is equal to 0.32. Okay. So this is that model incurs 0.32 bits. Everything is in bits. 0.32 bits extra surprise, because the actual entropy was only 0, but the model QA prediction brought in this extra 0.32 bits of surprise. Okay, so this is what it means. And now the second model, model B. Model B predicted the opposite, right? That it is 0.2 cat and 8 dog. So this is your cat and this is your dog. Here this is your cat and this is your dog. Opposite. Similarly, what will be this? T KL divergence of P will be equal to cross entropy minus the base. So this we calculated is 0. What is this QB? This cat and dog example we did earlier. This is here. 2.32 bits. Here we calculated this. Let's put that value because we've already calculated. So this will be equal to 2.32 minus 0. This is equal to 2.32. This is very, very high. Model B caused a lot of information loss because, as I mentioned, right, this KL divergence extra surprise or measures the information loss also. Okay, it measures the information loss also, and that will be measured in bits. So model A only caused 32 bits of information loss, and model B, it is causing 2.32 bits of information loss. And this is what it measures. The higher means the model is far away from the actual truth. The prediction is far away from the actual truth. Okay. I hope KL divergence is clear with this formula. Now let's move to Jensen and Shannon. This is good to know. You should know this. This is JS divergence. So JS divergence is JS divergence. JS divergence. What is JS divergence? So this is on the name of again two scientists, Jensen and Shannon. Jensen and Shannon divergence. So this is nothing. Jensen and JS divergence is nothing but an increment, a simple increment over KL divergence, which addresses some of the drawbacks of KL divergence. And what are those? So one thing is that, as I mentioned earlier, that this is not symmetric. That KL divergence of P and Q is not same as Q and P. Okay, so this Jensen and Shannon makes it symmetric. So this is a symmetric, solves this. This symmetric implies DKL JS. This is JS. DJS of PQ is equal to DJS of QP. This is how we write divergence. So this is symmetric. So it solves this. And this also okay. This is always finite. This also solves one more thing. This is always finite. Why so? Because if you see the formula of KL divergence, there is Px by Qx. So saying some condition probability of an event is 0. Like this is not equal to 0, and this is 0. If this is not equal to 0, this will be 0. This probability will become infinite, right? Because log of infinity will be infinity because it is a monotonic. So this term will become infinite. So the whole divergence will become infinite. So Jensen and Shannon divergence, it also solves this. It makes it finite. How does it do it? We'll see the formula and then it will become pretty obvious. So this is also always finite. It solves one more problem. It makes it symmetric, plus it solves that problem for KL divergence, and it makes it finite. So these are the two things it addresses. And how is it defined? So this is the average distance between KL divergence of two distributions and their mixture. So this is the average distance between KL divergence of two distributions P and Q and their mixture. So let's define it. So dJs of P and Q is equal to average distance. This is average distance of KL divergence. So half dKL of P given M plus half of average KL divergence. This is just an increment over KL divergence. Q given M. This is the average of the KL divergence of two distributions with respect to a mixture. And what is this mixture? How do we define this mixture? This mixture is half of P plus Q. This is the midway. This is half of P plus Q. So this is the average here, and this is half of P plus Q. So this will solve both that symmetrical problem, plus that will make it finite, because we are measuring it against a average model which will not become 0. This is average of these two. So if any one of them is non-zero, so this M term will not become 0. If P is not 0, means the average will not become 0. So this will never become 0. But the denominator will not become 0. Here M will not become 0. So this will not go to infinite. And also you will see this, that both the sides, it is half of the average. So this will be symmetrical if you do both the sides. Either you do this way or that way. Okay, so that's kind of self-explanatory. And let's do a simple problem, the same cat and dog problem, to understand this. For example, that cat and dog problem that we are discussing. So what is the truth? The probability is that this is with 1 probability cat and this is with 0 probability. So this is our truth. that there is a model which is trained to classify images, of cats and dogs, and the truth is I have a label that of one image that it is 100% cat and 0% dog. This is the truth, and I have labeled it. So the probability of it being a cat is 1, and probability of it being a dog is 0. So this is how my base is. And let's find the Janssen and Shannon divergence for this, the JS divergence. So this is a true label. So first of all, how do we go? Let's go step by step. So step 1. What is my step 1? That calculate the average first. So this is my average. So let's calculate the M first. So M is equal to half of P plus Q. Okay. And let's define. So let me talk of QA. The first model A is that it tells that 0.8 probability cat and this is dog. So this is cat and this is dog. So what will be the average of this? M will be equal to, this was P was 1 and 0, so this will be 1 plus 0.8 by 2 comma 0 plus 0.2 by 2. So this is equal to 0.9 comma 0.1. This is my M. So this second part is solved. Step 1, we go this, and then we'll calculate this term and take an average of this. Okay. Step 2 calculate this, step 3 calculate this, and step 4 take an average. We'll get it. So step 1 we got the M. Step 2, okay, let's calculate the KL divergence of M and P. So let's calculate calculate, let me write it down for you. dKL of P and M. This is equal to sigma, again sigma summation all of them. Okay, probability of X log of probability of X by M of X. This is how it is defined. So this is equal to, what are all the possibilities? There are only 2 possibilities, so we'll check that. So this is first is probability of getting a label 1. So that is coming from the actual distribution. So that is coming from P of X. So P of X is 1 into log of Px by Qx. Log of Px is 1 and log of Mx is 0.9 plus, everything is plus here. Okay. And the second term is 0. Actual, this is for cat and this is for dog. So actual probability of it being a dog is 0 into whatever the term is, but I'll write it down. So this is log of 0 by 0.1. Again, you see this is 0 log 0, this is undefined. So for computational purposes, we'll take it to be defined. We'll take a hack to make it 0. So what will be this first term be equal to? This is 1 will be 1. So this is log of 1 by 0.9. Everything is base 2. This is equal to, let's calculate this quickly. Log of base 2 1 by 0.9 is equal to 0.152. This is equal to 0.152 bits. This is your dKL of P and M. Step 3, the other part, dKL of Q and M. So this will be again summation of Px. Okay. Qx log of Qx by Mx, summation of this. So what is my probability of Q? What I have defined, whatever A is here, 0.8 and 0.2. Let's solve this. So Qx is now 0.8 into 0.8 by Mx is 0.9. We took the average, right? M is 0.9. This was 1 and 0.8. Its average is 0.9. So 0.0 and 0.2. Its average is 0.1. So qx, that is the actual, and I am predicting it using the average model. So 0.8, 0.8 by 0.9 plus this will be 0.2, the dog probability, into log of 0.2 by 0.1. This will be, so this is equal to, this is 0.2, 0.2, and this is all base 2. So it's become 0.2 by 2, this will become 2. So log 2 base 2, this will become 1. So this is equal to 0.8 into plus 0.2 into 1. So what is log of base 2? 0.8 by 0.9. So log of base 2, and instead of 1, now the second model predicts it as 0.8. So this is minus 0.169. So this is minus 0.169. Okay, 99. So let me take it as minus 0.17. That will be easier. And now I will do it as 0.17 into 0.17 into 0.8. So it becomes 0.136. So this is equal to minus 0.136 plus 0.2. This will be equal to 0.64. 0.064. Okay, so dKL of m is equal to 0.064. So final step, step 4, let's calculate JS divergence. So this is equal to dJs P of Q is equal to half of dKL P and M plus half of dKL Q and M. Okay, this is half of 0.152 plus 0.064. This is coming from here, 0.152, and this is 0.064, and this is equal to half. This will become finally half into 0.216. This is equal to 0.108. dJs P and Q is equal to 0.108. Okay, so this is, if you see the Janssens JS divergence for your first case. How much was the KL divergence? Just check. For the first case, this was 0.32 bits, and in JS divergence this is 0.108. it is less. Okay, so the lower the value means the closer are the two models. Okay, and if both the models become same thing with the case of KL divergence also. Say for example, what is the formula here? This is P and Q. So if both the models become same, Px and Qx will become same, so the KL divergence will become 0. Okay, I just want to remember. Okay, so lot of things. Let's do a quick summary of whatever we have discussed. So in today's class, in this video, we have discussed the main topics to understand with respect to machine learning was cross entropy, KL divergence. Okay, these are the two important topics which is used widely in machine learning. So the first thing, we try to understand it using information theory, because from these are the concepts borrowed from information theory. Okay, we try to understand it using information or surprise. So we define what is surprise factor. Surprise factor is the negative log of the probability of an event. More common the event, probability is higher. So this will become high probability, this will become negative, this will become, so say probability of head is 1. If I have a coin on which has heads on both the sides, so the probability of head will become 1. So this is common, there is no surprise whatever, so the surprise for this will become 0. And if I get a tail in this, so probability of tail will be 0, right? So the surprise for that will be infinity. So the common events, less surprise, so that's why this negative sign is there, and rare events, more surprise. So that's how we define surprise, and everything is based on surprise only now. So this is my surprise factor, negative of log px. Entropy, how did we define? This is the randomness, measure of randomness, or the average surprise of a distribution. What is the average surprise of a distribution? So average is expected value. So expected value of surprise. So surprise is given by log px, negative of log px, and expected value of that, expected value formula px into log of, into that whatever the function is, px into probability of that into log of px, and this x is coming from the distribution p. So this is your entropy formula, negative summation px log px. Okay, then we saw that probability of a fair coin. Okay, the surprise for a fair coin was 1 bit, and then finally the entropy of fair coin was 1 bit, and entropy of a biased coin, which for which the heads probability was 0.9, was 0.47 bits, which is very low as compared to 1 bit, because we know for sure that, almost sure that, it's not almost sure but very high confidence that I'll get a heads only. That's why the entropy or randomness is less. This is the measure, and 1 bit means highest for two possible outcomes, right? Two classes. This is the highest that we can get. That equal distribution, everything is uniform, then the randomness is higher. If we have equal chance of getting everything, means it is highly random. And as soon as you get biased around some value, so that surprise element gets less and less, as you saw in this biased coin example. That if I'm more biased towards head, means the surprise is less. That if I get heads, I am more or less, the randomness is less and the surprise will be less. But if I get a tails, only then the surprise will be more. But on an average, the randomness of this biased coin is less. So this is your entropy. Next topic is cross entropy. So this measures how surprised we are on an average when the truth is p and we measure it or predict it using q, and that's what gives the formula, that the actual distribution is coming from p, but by measure it using q, that's it. That's what our ML models are. So this gives your cross entropy, that is summation px into log of qx. This is a cross entropy. This is widely used in machine learning models to measure the cross entropy in the loss against when they have multi-class classification. Okay, and we saw a cat and dog example where the probability of where image of a cat and a dog was there. There was a model to classify given an image whether it's a cat or a dog. So we knew the label that 100% or p equal to 1, it is a cat, and 0 probability that it's a dog. And then we had two models and we measured the cross entropy for both the models. First model 80% cat, 20% dog prediction. For that the cross entropy was 0.32 bits. And there was a second model which said that 0.2 probability cat and 0.8 the reverse. The cross entropy is very high, means it is very surprised by the whatever it has predicted. Okay, sorry. So this is how the higher this means there is more cross entropy loss, there is more gap between the actual and the predicted. So this value should be as low as possible. Ideally both are same, then this will tend to 0, and the farther this is means the model is not predicting it correctly. Then an increment of that was KL divergence. This measures the delta or the difference between cross entropy and the actual entropy of the system. Actual entropy means that is the entropy in the system itself, that's the randomness in the system. But when I'm measuring it using a different model, I introduce more randomness on top of that. So the difference between the minimum possible randomness that is inherent in the system plus the randomness I have introduced because of the measurement I'm doing using another model or imperfect model. So the difference between them is what KL divergence measures. It measures the information loss between what is actually modeled by the actual distribution and with our predicted value. This is measuring the information loss here. That if it was measured using its own probability distribution, then this will become 0. We saw that if px and qx are same, if both the models are same, then this information loss will become 0. But because I'm using an imperfect or a close enough model, that is giving me some information loss, and that's what KL divergence measures, or the extra randomness we are adding to the system. This is also again measured in terms of bits. The formula is px log px by qx for discrete, and for the continuous it just becomes integral here. Okay, it is not symmetric. The two problems we saw, that it is not symmetric and it can become infinite if this is not equal to 0 and this is equal to 0. So this will become infinite. In that case, we saw this example of the cat and dog. Okay, so there are two issues with this that we saw obviously, and then we went to JS divergence, which solved both the problems of this. It is symmetric. Okay, so DJS of PQ is same as DJS of QP, the other way around, and then it takes the average of two values and it takes the average model or another target model in the middle. Okay, and it uses that as a middle ground for, or a mixture model. It's called mixture for measuring it. This is the formula. So this is what it makes it symmetric, and then this M will never become 0, because if P is not 0, this average will exist. It will not be equal to 0. P or Q means P will, if P is non-zero, then this average will exist. So you measure this KL divergence, then none of the terms, this term will not be 0 and this will become 0. Okay, so that infinity problem is solved. So this will become finite. And then we saw with the cat and dog example here, and using that cat and dog example, we found out that JS divergence, we for the steps also, step 1, step 2. Okay, first we found out the mixture model, that is the average of two models. Then we calculated the KL divergence for each of the distribution P and Q, and finally we put it in the formula. We took the average of it, and then we got the JS divergence, and we saw that this is less than KL divergence. Okay, I hope all these concepts are very clear. Thanks for watching. Have a good day. Bye for now.